About the circuits, there were two kinds of questions. One is this one. This is the one example that I would like to discuss. And the second example that I would like to discuss will be this one. Now, if you have any other questions, do you want any other problems that we should discuss besides these two? And there's also, which one? The homework question. Okay, there's also this mutual inductance problem. This one. Now, by the way, this symbol over here doesn't mean that we attach a solenoid over there. We don't have these two solenoids. What we have over here is we have a circuit element. This whole thing is a single circuit element which has 4 pins, and there is a mutual inductance is non-zero between the pairs of pins. There was one missing information in the problem, because depending on whether you attach these 2 pins like this or the other way around, the current over here will run either in one direction or the other direction. Both answers will be accepted. It will only modify the mutual inductance. The value of the mutual inductance will reflect what is, if there is a material or not. Okay, this is the common symbol. Okay, this is your mutual inductor. Now let's start with the simple one. This one. Well, I don't know, we probably have discussed like 3-4 different points of view of attacking the same problem. All are true, all are valid. You can just pick any one of them. Now, the first thing you have to do, if the directions of the currents are not shown, just pick up some direction. Which one? Who cares? It's just arbitrary. If you find a negative current, it will just only tell you that it will be moving in the other direction. So let's say this is the direction of the current I. Now we can just follow the direction of the current and discuss how much work is done on a positive charge as we go around the loop. Now, okay, let's see. We go from A, B, C, D. From D to A. As we go from D to A, how much work is done on our charge? Or how much energy does it lose as we go from D to A? Okay, this is the amount of energy the positive charge will acquire as we go from D to A. We are writing the total energy gained by the charge as we go from D to A. Since we are writing the total energy gain as the charge is moving in the direction of the current across the resistor, it will lose energy by this IR. That is why we have this minus sign. Now let's go from A to B. How much energy does our positive charge gain as we go from A to B? Plus V. You see, this is the small one is the negative terminal, and the large one is the positive terminal. So the battery, it just takes energy, takes low energy charge objects from the negative terminal and gives away high energy positive charge objects in the positive terminal. So from A to B, the positive charges gain energy given by this V, plus V. Now the tricky part is kind of this one. It is always L di by dt. This should be equal to 0. Now the question is it positive or negative? Now to determine whether it is positive or negative, you can just assume that some given sign for di by dt. Now you can just assume, let's say, di by dt is positive. So I is increasing in time. Now the inductor will always try to resist changes. So I will try to resist an increase in the current. So it will try to run a current if di by dt is positive. Now this inductor will try to run a current in the counterclockwise sense. So if it is trying to run a current in the counterclockwise sense, you can just think of this inductor as a kind of a battery with this one is the positive terminal, this one is the negative terminal. It's kind of like that because you see a battery with positive terminal connected here, negative terminal connected here, will try to run a current in this direction. And if di by dt is positive, the inductor will also try to run a current in the same direction. In that sense, they are similar. But in that case, from C to D, how much energy does our positive charge gain? It loses an energy. It's from the high potential region to a low potential region, so it is losing energy, and the amount of energy it loses is the absolute value of this one, but this is already positive. So since it is losing and we are writing the gains in the positive charge, this is our equation. No. Initially, do you see, if the current is, you can say, is it possible to have a constant current? Well, if the current is constant, this term is 0, then the current is nothing but V over R. So if there's a constant, it's possible to have a constant current running in this circuit, and then the current running in the circuit will be just V over R. No problem with that. But at the instant that you connect the battery, initially there is 0 current running in the battery. Sooner or later we will have a current V over R running through the battery. There should be a time-dependent current at some time. Because initially it was 0, finally it has the value V over R. It should be changing in that interval. Now, how does it change? Well, the change is given by this expression. This expression is valid even if di by dt is 0. Well, if the current is constant, this term is 0, the inductor just doesn't exist over there. Now, another thing that you can think right over here is, let's say, if you want to pass, rather than having this constant V over here, let's say a time-dependent potential. Time-dependent with some frequency omega. In that case, if omega is very fast, then this term will be 0. It will be very large. Well, it will be a very large frequency times the amplitude of the current, but that should be more or less has some value, some fixed value. That means the current cannot be that big. So for a very large oscillating potentials, the inductor just behaves like an insulator. For slowly varying potentials, well, this derivative is negligible. It's as if this term is not there at all. So for small, slowly varying potentials, the inductor just behaves like it is a short circuit, which is in opposite to the behavior of a capacitor. Remember, a capacitor for fast varying sources, fast varying currents, if the current is changing very fast, the capacitor just behaves as if it is not there, because since the direction of the current will be changing very fast, the capacitor will not have any time to be charged. If it cannot be charged, it doesn't create any potential difference. It's as if it is not there. But for slowly varying potentials, for slowly varying currents, well, the capacitor will be fully charged, and once it is fully charged, it will not allow any more current to pass through. So for slowly varying currents, it will be as if it's an open circuit. The capacitor will just behave as an open circuit. There won't be much current passing through the capacitor. Okay, any questions on this one? Now let's go to this parallel one. Okay, the first thing you should do is again just choose some direction for your currents. Let's say this is I, this is I1, this is I2. Now for the capacitor, you also have to choose the polarity of the capacitor, which one you call the positive plate. Now we have our directions. Now, again, let's follow positive charges. Now, one equation is, of course, at this point we have the conservation of charge. I is equal to I1 plus I2. So the total charge entering this point should be equal to the total charge leaving that point. And then, if you just imagine a positive charge, there are many loops that you can follow. You can just go around this wire, or you can just go around this wire, or if you want, you can even go around this loop as you wish. They should all give the same answer. Now, let's go around this one first. A, B, C, D, E, F, G. So we started from A, there is no resistance over here, B, then we go to C. Now across the inductor. Okay, it is always L di2 by dt. Now the question is, will it be positive or negative? Let's just assume that at a given instant, I2 is increasing. So if I2 is increasing, again, the inductor will try to resist this change. So it will try to run a current in this direction, in the opposite direction. So it will be as if this is the positive terminal, this is the negative terminal at that instant. At some other time, I2 might be decreasing, then these polarities will be different. But let's say that at this instant, I2 is increasing, because whatever sign is over here, it will have the same sign all the time. So if we can determine the sign at a given instant at which I2 is increasing, it will have the same sign even if I2 is decreasing. Now, if I2 is increasing, this is the positive, this is the negative terminal. So as we are going around it, so how much energy does this positive charge gain as it passes through the inductor? It will be, well, it is losing energy, so its energy gain will be negative. Well, this number is positive because I2 is increasing, so we should put a minus sign over there. Okay, across the resistor, how much energy does it gain? Minus I2R2. Okay, minus I2R2 across this resistor. Then we have across this resistor minus I times R1. That is how much it gains. And then finally, let's say plus epsilon. This is equal to 0. Well, since this is changing sign constantly, it doesn't really matter whether you put a minus sign or a plus sign over there. The only thing you have to be careful about is that if, as you are passing from G to A, if you are putting a plus epsilon in one equation, you have to put plus epsilon in every equation as you are going from G to A. You have to be consistent, but the sign, overall sign doesn't really matter. Because we are right, if we are imagining we take a positive charge running with this current, and we are writing the energy gained by this charge. So as it goes from F to G across the resistor, it will be losing energy. So its energy gain is minus the amount of energy it lost. Okay, this is one of the equations we have. Now, since we have three unknowns, well, at least three unknowns for the time being, we have to write at least three equations. This is one of our equations. This is the second equation. And now we need to write the third equation. And the third equation we can just obtain by going from A to B. This is H, this is J, A, B, H, J, F, G. And then back to A. I will be just going, start from here, I will go around this upper path and then back to A. From A to B, nothing, no resistance, nothing. Now, from this side to the other side, this is the positive terminal. How much energy does my positive charge gain? Minus Q over C, because we go from the positive plate to the negative plate, so it is minus Q over C. Well, now I have a fourth unknown. Q is also an unknown, so we have to write 4 equations now. 3 won't be enough. But we will think of that later on. Okay, from the positive to the negative terminal, this is how much energy gained, my hypothetical positive charge, and now for across R3, minus I1 R3, across R1, minus I R1 plus epsilon. This should also be equal to 0. This is my third equation. Since I put a plus epsilon over here, I have to put a plus epsilon over here too. And finally, I know that Q is related to I1. Is there a plus sign or a minus sign? If I1 is positive, is Q increasing or decreasing? If I1 is positive, then Q should be increasing, so dQ by dt should be equal to I1, plus, with a plus sign. If I1 is positive, dQ by dt should also be positive. So now we have 1, 2, 3, 4 equations. Now we can look at certain limiting cases. For example, we can say that what happens when omega is very large. Well, when omega is very large, in that case we know that the inductor would prevent any current to pass through it. I2 will be 0. When omega goes to infinity, I2 will be 0. But that means I1 will be equal to I. When omega is very large, the inductor just behaves as if it is open circuit. So there's no I2. If I2 is 0, capital I and I1, they are equal. And when omega is very large, the capacitor just behaves as if it doesn't exist. It is short circuit. And if the capacitor doesn't exist, this line doesn't exist. The capacitor is just short circuit. So I have a single circuit with 2 resistors in series. So the current passing through it will be just epsilon over R1 plus R3. If omega is very large. Why did we get I2 equal to 0? Well, you see, omega is very large. So the inductor will just behave as if it is open circuit. There is no current running through it. So I2 doesn't exist. Now, in this limit, we already know the solution. We don't need to worry about solving all those 4 equations to obtain the current as a function of time if the frequency is very large. If the frequency is very large, this will be the current running through our system. Now we can look at the other limit. Well, you see, if omega is huge, that is the direction of the current is changing very fast. But if the direction of the current is changing very fast, the capacitor doesn't have enough time to be charged. So the charge in the capacitor will be negligible at all times. So if there's no charge in the capacitor, there's no potential difference across the terminals of the capacitor. No? Now you see, since the current is constantly changing directions, at one instant the charges act as if they are going into the capacitor, right in the next moment they will be moving out of the capacitor. And then in and out, so they will not accumulate. They will not have enough time to accumulate in the capacitor. Okay, let's look at the other limit. Omega goes to 0. It is almost a DC circuit. And of course, in all of these, we are waiting for a sufficiently long time. So we close the circuit, we wait for some time, and then these will be the currents. Now, if omega is equal to 0, now what will happen is we are applying a constant potential. In a constant potential, again, we wait for a sufficiently long time. In that case, the capacitor will be full. If the capacitor will be full, it will behave as if it is an open circuit. There won't be any I1. I1 is 0 after we wait for a long enough time. I2 is equal to I, which will be equal to. And again, if we wait for a sufficiently long time, this is almost a constant. Since omega is very small, this is almost a constant. So, and we wait for a sufficiently long time so that any changes in the current they will be smooth. Since the changes are very slow, the inductor will not do anything because the current is changing very, very slowly. It's almost as if it's not changing. So the capacitor is full. There won't be any charge passing through this branch, this wire. The inductor will be as if it doesn't exist. So we have a single circuit with a constant potential difference over here and two resistors in series. And hence the current will be epsilon over R1 plus R2 this time. Again, in this limiting cases, we know what the answer should be. Now in between, for a value of omega, for a medium value of omega, not very large, not very small, of course in that case we have to solve all these four equations. And that will tell you how the current will change as a function of time. This is not on the RLC circuit that we have studied. If you remember, in the RLC circuit that we studied, it was just we calculated the impedance and the phase shift using that impedance. But the solution in this case, well, you can still obtain the solution. No. The solution will be complicated. You need to solve all these four equations. If this wasn't over here, then it would have been an easier solution. No. You see, the RLC circuit that we studied, the resistors and the capacitors and the inductors and the power supply all were connected in series. Here, they are not connected in series. Now, if there's no inductor over here, the omega, very small omega limit will not change, because in the very small omega change limit, the inductor just behaves as if it is not there. So it's just a short circuit. But the omega infinity limit will be different, because in the omega infinity limit, if you put an inductor over here, there won't be any current passing through it. But if the inductor is not here, then there will be a current passing through this. If the inductor is not in the omega infinity limit, yes. Now in that limit, if there is no inductor, in the omega infinity limit, what will happen is that the capacitor will be as if it's not there. So you have two resistors in parallel, which are then connected in series to a third resistor. Oh, this one. So we just choose this loop. Well, let's write it down. So let's see, from C to H to J to D, and then back C. Okay, we start from here, we go to H, nothing changes. Okay, from H to J, we first pass across the capacitor. How much energy does the positive charge lose? Let's say lose this time. Q over C. Then from this point across the resistor, it will lose I1 times R3. Now this time I'm not writing the energy gain, but the energy lost. So that's why I have the plus signs in both of them. Then we go across this resistor, but the current is passing in the opposite direction, so the amount of energy it loses will be minus I2 R2. And across the capacitor, the amount of energy it will lose will be minus, because it's going from minus to plus, minus L di2 by dt, equal to 0. Which one? Now, in this equation, I'm writing the energy lost. No, that was energy gain. Now, let's look at this equation. Let's remember the other two equations. Let me also take these two equations. This was one equation we had. This is the other equation we had. Let's take this one and subtract this one. We have the second equation minus the first equation. Well, these two terms are common, so they will just cancel each other. So I will have minus L di2 by dt, this one, minus I2 R2, this one, plus Q over C plus I1 R3. So this equation, this is a single equation, is not an independent equation from these two. They are basically the same equation. So this equation is nothing but the difference of these two. And that should be because we have 4 unknowns, we should have only 4 equations. An independent fifth equation will be too much. We shouldn't have any other fifth equation. And this is an example where we don't really have any fifth equation. All the other equations that you can write by considering all possible ways that you can start from a point and come back to the same point, they will all be, you can all write them in terms of these two equations only. Which ones? Well, there are two things. One of them is, okay, the I2, the direction of I2 is the same, but in this equation, we are moving from C to D. In this one, we are going from D to C. Okay, fine. Well, that is how we are just counting the, you see, we are just summing the energy lost from this point to this point. It lost the energy, Q over C, from this one to this one. This is how much it lost. From this one to this one, it gained energy. And gain energy by this much. But again, we can write a minus loss. So that's why I put a minus sign over here. Other questions? True. Why? No, epsilon is not zero. Epsilon is just a constant. So that's what we call a DC current. The potential, the voltage of the power source or the battery in that case will be just a constant, V. Other questions on this one? Okay, now let's look at this example. First, again, you have to choose some direction for the currents. I1, I2, this is epsilon. Okay, let's also give some names. A, B, C, D, E, F, G, H. Now, let's go from C to D to A to B. This is, let's say, this is R1, this is R2. Now, from C to D, how much energy does our point unit charge gain? Minus I2, R2. From D to A, let's say epsilon. From A to B, nothing. And then from B to C. Now that is both a self-inductor. Now let's say I2 is increasing. If I2 is increasing, it will just, this I2 is increasing, it will try to run a current in the opposite direction. So this will behave like the positive terminal, this will behave like the negative terminal. So as we go from B to C, the energy gain will be minus L di1 by dt. This is one contribution to the energy gain. Now the problem is, if I want, this is I1, no, this is I2, this is I2. This was all of it if this was just an ordinary inductor. Now the problem is this is not an ordinary inductor. This is there's a two coupled inductors over there. So we have this mutual inductance. And this, even if I2 was just constant and I1 was changing, this would create some EMF in this inductor, only because of the mutual inductance between the two. And that EMF will be M di1 by dt. Now the problem is, will it be positive or negative? Well, it will depend on how you connect these wires. So if you would connect it in one direction, it will be a positive sign. If you would just change the circuitry so that you connect this wire to this terminal and this wire to the top terminal, it will behave differently. Because let's say if I1 is increasing, then due to the self-inductance over here, it will try to push a current in the downward direction. Depending on the wiring, it might push a current in the downward direction or the upward direction. So that is an information that is missing in the question. Now let us assume that if I1 is increasing, then that is I1 is increasing in this direction. Let's just assume that this one it will induce an EMF with this polarity, plus and minus. It's the same polarity. So in that case, this will also be a minus. Okay, this is one of our equations. Now, why this is minus? It should be a given information. So if this is running if this is I1 is increasing in this direction, then it will try to create a current in this direction in the other circuit. That depends on how this thing over here is wired. So that's an information that should have been given. It doesn't have to be. It depends on how this thing is wired. Okay, you see, this sign over here is a property of the wiring of this thing. I don't know how that is wired. In the question, it was not given. I'm just saying, let's just assume. There are two possibilities. Let's just study the case in which this sign over here is minus. That means that, this device over here is basically, it will be such a black box. It will look something like this. And you have to be told if the current is running in between these two in this direction and increasing, in that case, the current in this wire will be pushed in this direction. It's an information that has to be given, which I didn't give in the homework question. And that's what I'm saying. Let's just choose it to be the minus sign. Now, this sign will fix the equation, this sign in the other equation. Let's see, let's go the other way now. From G, from E to F to G to H, and then back to E. Okay, from E to F, nothing. F to G, how much energy gain? From E to F, F to G, energy gain will be minus I1 R1. I'm writing the energy gain. You can write energy loss. It's the same thing, it's just the overall minus sign. This is the energy gain over here. Now from H to E. There is the self-inductance. Let's say I1 is also increasing. Now, if I1 is increasing, it will resist. It will try to resist. So this will be plus, this will be minus if I1 is increasing. So since we are writing the energy gain from H to E, it will be minus L di1 by dt. This is due to the self-inductance of the circuit element over here. Now we come to the mutual inductance. There will be also plus M di2 by dt equals 0. Now, will it be plus or minus? Now, you see, these signs over here are due to the self-inductances, not the mutual inductance. So let me erase them. So let's see. So what this term tells me is, so we already said that if I1 is increasing, this device will create an I2 in the opposite direction, in this direction. If I1 is increasing in this direction, this will be running in the opposite direction. Now, if I2 is increasing in this direction, what should be the direction of the current in this one? If I2 is increasing in this direction, this should also be increasing in this direction. So the energy gain as we go from H to E, it will be plus. Now, this mutual inductance is quite a symmetrical thing in the sense that if I1 is increasing in this direction, and in that case it is creating a current in the same direction, it should be also true for I2. If I2 is increasing in this direction, then it should be creating a current in the other one in the same direction. So due to this mutual inductance, this one over here will try to run a current in the counterclockwise sense. Now, if we are going in the clockwise sense, then we are gaining an energy by this much. So that's why we have a plus over here. Now we have two unknowns, two equations you need to solve if you want to determine how I1 and I2 change as a function of time. Which we will not do it. Yes, you will learn how to solve such equations next year. Other questions? Of course, this M will change depending on how this thing is made up. Depending on whether there is a solenoid, two solenoids, or whether there is a material inside or not. They are all in this parameter M. Well, just add the separate terms. The capacitors here and here. Well, you see, if you add a capacitor, wherever you add, let's say there's a current I, let's say this is positive, this is negative, so let's say this has a charge Q. As you move in this direction, the energy gain will be minus Q over C, and then dQ by dt will be I. I mean, these rules do not change depending on whichever elements you have in the circuit. So if you are crossing a capacitor from this point to the other point, from the positive plate to the negative plate, and you are writing the energy gain by this unit charge, the energy gain will be minus Q over C. And if this is the direction of I, this is how you assign the positive and negative place, and this is how Q and I will be related. Whether there are some other inductors or diodes or any other sophisticated circuit elements somewhere else, I don't care. These two contributions will be the same. You see, this is not something that you can separate. This is just such a circuit element with 4 legs. You cannot play with it. Now, if you change how these solenoids or the loops inside this device changes, it will change this mutual inductance, and all the changes you make in the circuitry will be reflected in this different value of the mutual inductance. The mutual inductance. Other questions? You see, here I don't have 2 solenoids. I don't know what I have inside. It's just a device that I'm given. which has this property that if you pass a current through the two terminals, then the other two legs, there will be some potential difference. That's what I know. Now, can you build such a thing using solenoids? Yes, you can build such a thing using solenoids. And I would rather wrap one solenoid around the other one rather than putting these two solenoids side by side. Well, if they are like this, in the ideal solenoid case, the mutual inductance would be 0. Because if you run a current in one of them, it will not create a flux in the other one. Just add it over here, plus epsilon. Mutual inductance depends only on the geometry of the configuration of the loops. It doesn't depend on anything else. You see, whatever we are doing in these circuits is just bringing each circuit element side by side and adding the contributions. The properties of each one of the circuit elements doesn't depend on what you put next to it. It's independent. Okay, any last questions? Okay, see you on Monday. Now, I will be correcting some of the mistakes in the final checklist. Just wait until like 7 o'clock in the evening before sending me an email. After 7, I will probably already have sent an email to all of you. If you still have problems, send me an email. I will resolve them.